Welcome to video 6B, I believe this one is. And in this video, we're going to keep working with our circles. I got to go back a page here, 6B. And we're going to do some circumference and some area. Then we're going to talk about some other angles and then some tangents, we call them. So circumference and area should be a review for you because these are covered in middle school, but they're good to repeat. We've already had to use the area of a circle in chapter 5 anyway, so that should be fresh. Circumference of a circle is basically its perimeter. Gets given a different name because perimeter kind of means to add up all the sides, and this circle doesn't have any sides, but we're still looking at the distance around the circle. And circumference, the distance around, C, is equal to 2 pi r. And you'll notice that the r is in there just once, and that'll give you the distance around the circle. If I were to start here and walk around it, how far did I go? That's circumference. Area is if I were to get out some paint and paint this, how many square units did I paint? So it's two-dimensional. It's not traveling around and doing a length in just one-dimensional. It's two-dimensional. Suppose I was doing square inches. I want to know how many little square inch things would it take for me to piece together to cover the entire circle. That's what area means. It's got two dimensions. So the area formula, you'll see r in there twice for the two dimensions. So it's pi r squared. Those need to be memorized. So nice and easy, find the area, but we're going to leave our answer exact. And again, I've told you sometimes that'll be phrased as in terms of pi. Area is equal to pi times radius squared. When I'm asked to leave it exact, because nobody knows pi, it goes on forever, never repeats. That's called an irrational number. You've been taught to round it to 3.14, but the minute you round it, you're no longer exact. So when it asks for exact answers, we just write pi in them, and we'd go do the rest of it. 12 squared is never 24. It's 12 times 12, which is 144. So we'd say the exact area of this is 144 times pi inches squared for area. The labels are important in these. Circumference. Circumference is equal to 2 times pi times the radius, a singular dimension. So I do 2 times pi times the radius, which they gave me. If they gave me the diameter, I'd cut it in half. I'm going to leave pi in my answer, and I'm going to go do the rest of it. 2 times 8 is 16. This is just a length. It's how far did I walk. I walk in miles, not in square miles. So I label that 16 pi miles. And that's all we're going to do with those. Those should be review for you. Next, we're going to figure out what the radius is when we know the circumference. We're still going to write the formula down. It's really helpful. Take out your map. Formulas are maps, and when you don't write them down, it's like trying to get somewhere without the map. You're probably going to take a wrong turn unless you've traveled that route many, many times. So circumference is equal to 2 pi r. They gave me the circumference, so I'm going to replace that. I'm going to solve this for r, so I'm going to undo multiply by 2 by dividing by 2. When I divide both sides by 2, I would get 62 divided by 2, which is 31.4, is equal to pi times my radius. Again, pi is a number. I'm multiplying it by r, so I'm going to divide both sides by pi. Now, if you're using 3.14 for pi, you're going to get an exact 10. That's really not what pi is, so I would suggest you use your calculator and just do 31.4 divided by, and then use that second caret key, and you're going to get 9.99 repeated, which is really 10. So we're going to say r is about 10, but again, the minute you round, you're a little bit off, right? So here we go. Where's my map? Area is pi r squared according to my formula, also known as my map. On this one, they gave me the area, so I'm going to dump it right in, and I've got 201.1 is equal to pi times my radius squared. And again, I've got to isolate that radius. So the first thing I'm going to do is get rid of the pi. by dividing both sides by pi, because it's pi times the radius squared. Gone, gone. I'm going to go to my calculator. I'm going to do 201.1 divided by pi, and I get about 64. So we're going to round that to the tenths, but when I round, it's actually 64.01211.811. 64 is equal to the radius squared. How do I undo squaring? This is like in the Pythagorean theorem when we ended up getting, when we're all done, c squared equals 25. What's c? And we square root both sides. Same thing here. I'm going to square root both sides. It'll give me an r over here and an 8 over here. So my radius is 8, and what's my label? Inches. Again, a radii is a length. We've got 3 different labels going on. Length, 1 foot. 2-dimensional or area, 1 foot squared. 3-dimensional or volume, 1 foot cubed. So know how to label those correctly. An improper label is really deadly in these. Inscribed angles, a little bit of vocabulary for you for inscribed angles. What an inscribed angle will look like is you have a circle. We've already talked about central angles, that they hit in the center, that their measures are equal to the arcs that they cut off. An inscribed angle goes and hits on the circle. So not in the center, but on it. And what happens with that, I'm going to put this dot a little smaller so you can see it. And let's label this. So let's suppose we've got AB, and then we've got C over here. So we've got an inscribed angle, angle ACB is an inscribed angle. I'm just going to point at it. When we talk about its measure as compared to the measure of the arc it cuts off, the intercepted arc, so we have this angle here, and we have the arc being cut off by the chords that make up that angle, they are not equal. The central angle, and don't draw this, just I don't want you to clutter yours, but in purple don't draw it. If I draw a central angle, that measure equals the measure of the arc it cuts off. So if this is an 80-degree arc, this is an 80-degree angle. But when I pull that back farther, like I've done here, like this, you'll see that that angle shrinks. And you can see it looks like it's about half of the purple angle, and it is. So we have a little theorem that says the measure of an inscribed angle is equal to 1/2 the measure of the arc it cuts off. And there's a lot of alphabet soup going on here, so you might want to write that in words. That inscribed equals 1/2 arc, or the arc is twice the inscribed. Let's go put a little angle measure on there now. That would be 40. So it depends on what you ask for, angle or arc. So let's go take a look. Find the measure of the arc or angle indicated. Here's the angle. Oh, it's the one I just put up there. Oh well, poor choice on my part. Anyway, the angle is equal to 1/2. I had a phone call, so I had to pause this. So I think I was saying that this is 1/2 of the arc that it cuts off. So that would be the measure of angle CAB, which I could actually call angle A, since it's the only one in there, is equal to 1/2 of the arc, or 40 degrees. Easy peasy. Next one, solve for x. This one's got a little bit more work I need to put in, but again, my x is out here. It's some part of, it's in an arc measure. So let's go see what I can do. And again, it's like a puzzle. Let's see what I can figure out. Why did they tell me that this is 110? Probably so that I could go out here and use my inscribed angle relationship, where the angle is 1/2 of the arc it cuts off. 110 is 1/2 of what? Well, double it and you'll know. So what I know is that red part is 220. I also know that this yellow part is 50. So the only part remaining to complete the circle is this blue part of the arc. And we know that a full rotation around a circle is 360 degrees. So what I can do is say, well, I know if I go all the way around, that's 360 degrees arc measure. So I'm going to remove the 50, the yellow part, and I get 310 left. Well, then I'm going to remove the 220, the red part, and I get 90 left. So the only thing left for the blue arc is 90 degrees. So 90 degrees would have to equal 30x, which means x is going to have to equal 3. Let's go see if that looks good. Let me grab a purple here. So I'm going to erase everything on here. And let's go draw that arc, which I'm saying is 90 degrees, which should be equal to the central angle. Does that look good? Looks really good, doesn't it? So I like it. We are done with that one. Let's go see what's next in line on the next page. Next up, we're going to be working with, we got 3 topics in here, tangents to circles. So this is worthy again of a little bit of vocabulary. So what I'd like you to do is go off to the side over here and let's talk about what a tangent is. When you're tangent to somebody, it means you're next to them. When we talk about a tangent to a circle, it means it touches it once on the exterior. Remember, a chord touches it once on the inside. What a tangent does is it nicks the circle at one spot on the outside. This would be called a tangent segment. And if I were to have that go all the way across in yellow, which I'm not going to have you draw, but just watch me do it. If I were to do this, this is called a tangent line. So what we know, back to here, my tangent segment, this right here, so I'm going to write tangent, and you should draw this as well. This is called a point of tangency. It's kind of like, I'm not touching you. Yes, you are. Point of tangency right there. And so we're going to deal with a couple relationships between tangents and circles. Let's divide our concept box into 2 pieces and go throw a circle on here. Our first relationship is when I take a circle and I draw a tangent to that circle. I'm going to make this a little bit more rounded up here. It still doesn't look, I mean, it started off being a super circle and then it went a little haywire. But let's go here and make this be a point of tangency. And I'm going to draw a tangent segment maybe out to here. So that's a tangent segment. Then what I'm going to do is draw the radius to the point of tangency. So this is my radius. This is my tangent. So I've got a radius drawn to the point of tangency. There's a theorem, doesn't matter what its name is or what its number is, just that you can use its relationship, that says that those are perpendicular, that they meet at a right angle. So the tangent line is perpendicular to the radius, and again, that's at the point of tangency. Let's do this. Good enough. That'll do her. So my next circle over here, and again, by the way, I'm going to just show you something. What's going to usually happen is you're going to complete that, make a triangle, and you're going to be asked some questions where you need to use the Pythagorean theorem, just so's you knows. All right, so next up, we've also got another, so let's see if I can draw another decent circle. That says if you go outside the circle and draw the tangents to the circle, there'll always be 2. There's one tangent. See, if I head in here, that's not called tangent, because if you keep going forever, it can only hit it once. That's actually called a secant when you hit it twice. In order for me to only hit the circle one time from this exterior point, I'm going to have to hit right about here. And the theorem says that these 2 pieces are always going to be congruent. So let's put some numbers on it. If that's 5, then that's 5. So we're going to be using those 2 properties to find some missing links. First one, find the segment indicated. Well, here's the deal. I've got a tangent line and a radius meeting at the point of tangency. This one right here says that those meet at a perpendicularly or at a right angle. So for me to get question mark, I've got the hypotenuse of a right triangle. So what I know is that for me to get this yellow length, I'm going to have to do a squared, leg squared, plus leg squared is equal to the hypotenuse squared, which is a question mark. I'm going to call it C. So I know that 144, 12 times 12, plus 256, 16 times 16, has to equal the square of my missing length. When I add these up, I get 400. That has to equal the square of my missing length. So what times itself equals 400? You can probably tell that it's 20, but again, remember to undo a square, we square root. So 20 would be the length of C. So right here, that whole yellow length is 20. What if I asked you, let's add to this question, what if I wanted just the green length? How could I get that? Remember that the radii of all circles are congruent. It's like the spokes of a wheel. So if this is 12 from here to here, this is 12 from here to here. So if the whole way is 20, I could just do 20 minus 12, and that little green piece would be 8. So that's just a little added enrichment to that problem. Now I'm being asked to find the perimeter of the polygon. The polygon is that triangle. I've got that second situation going on up here, right here, where I can say that these two tangents segments, whoopsie, are always the same length. And let's go use that property to figure out how to get all the way around the triangle. So let's go. On the first part, you can see you've got a 10.5 over here. Well, let me draw in yellow. If this is 10.5, then the other tangent is 10.5. If this is 11.2, then the other tangent is 11.2. Don't know this one or this one. I know they're the same, but they did tell me that that whole length over there is 23.2. So if this whole thing is 23.2, if I do 23.2, the blue, minus 11.2, this little purple piece right here, I'll have the rest of it, and that equals 12. So what I know is this piece is 12, which means the other tangent piece is also 12. So now I've got two yellows, two purples, and two reds that make up the perimeter distance around that polygon or that triangle. So let's go add them up. We have 10.5 plus 10.5, the two yellows, which were congruent from the get-go. Then I've got the 11.2 plus the other 11.2, or I could just even do, yeah, let's just travel and let's just keep it clear here. And then I've got the two reds, which are both 12. If you go add all that up, you'll get the grand distance around that polygon. And I don't feel like adding it up, so you can do it. I believe that might be the end of this video, but just to make sure, because I don't want to end it if it's not the end. Oh, there is one more. Good thing I checked. So the last one, looking for the measure of an angle outside of there. This is going to deal with some other properties that we've got going. But if you look at it, we've got that radius drawn to the point of tangency right here, connected to the tangent, which I know that's a right angle. Similarly, again, using that first property, I know this is a right angle. Well, now we're going to use something from one of the other units that we've covered in here, and that is, what do the angles in a quadrilateral add up to? A triangle, the angles add up to 180. For a quadrilateral, they add up to 360. So I've got the 117 that they gave me, the two 90s that I was able to figure out from that first relationship that we did in the concept box. So I've got another 90 right here. My smartboard's on a little delay, so let's see if it'll take long. Otherwise, you just do 117 plus the 90 plus the 90, and you're going to add that all up. So you have 117 plus 90 plus 90, which gives you a grand total of 297. So what you know is that U and you take up 297 degrees of the 360 that's in every quadrilateral. So if I just do 360 minus 297, I will get the missing angle, and that will give me 63 degrees. And that's the end of this video, and you'll go work on these and have me sign off when you're done with that chunk. We are nearing the end, so good job, guys. Peace out.